So this is problem 74 from chapter 27. 74. So here we have a loop, a square loop that's in a uniform, unidirectional but non-uniform magnetic field. So let's draw what's given in the problem. So this is our coordinate system, y and x, and from this point B we have a square loop where one side is just A, the other side is also A. So there's some magnetic field. Here the direction is given as towards us. They're saying that the magnetic field is directed along Z with a magnitude that varies with x according to B equals B naught. Times 1 minus x minus b, x over b, minus x over b. Now this is a little bit misleading. They are referring to this as the magnitude. The magnitude is always positive, okay? And depending on the sign of b naught, this is negative either when x is larger than b or when x is smaller than b, but either way, at some point it's going to be negative. So this can't be the magnitude. What I suspect is that what they mean is that this is the z component of the magnetic field. Okay, so that's what I'm going to go along with. Fine. And so this is our square loop, this is our magnetic field, and we are asked to calculate an expression for the net force on the loop. Right? So, on the loop. Okay, so I think it makes sense that we divide this into 4 parts. So this is also A, not Q. So the 4 sides of the square is going to feel some force, and all of those can be calculated by means of some integrals. So I'm going to divide it into that form. The direction of the current, by the way, is given this way. So let's start from the left hand side. Okay, so what is the magnitude of the magnetic field at x equals b? It's 0. Okay? This fraction gives 1, 1 minus 1 is 0. So there is no magnetic field, there is no force on the left hand side of this loop. Now, if you calculate the force on this part and the force on that part, we are going to find that they're going to cancel each other, right? So if you choose just 2 little parts, or it's not to be sure, to make an explicit calculation, you need to take an integral and everything, because the magnetic field is varying as you move in x direction, and it's going to move along this line segment as well. But for each part, there's going to be some small force acting on these 2 corresponding sides, and they're going to cancel each other. That's my claim. Now let's calculate the magnetic field over here. So we'll go this way. So first of all, by the way, after x exceeds b, this is going to flip sign. So over here, if this is positive, over there, this is going to be in the opposite direction. Okay. So this is my I, this is my magnetic field. The little force is going to be acting this way, whereas here the current is this way and the force is going to be acting downwards. So these two are going to cancel each other, and the net force coming from these 2 segments of the square is going to be 0. So we are left with the force that's acting on this part, that is going to be to the left. Okay. And I don't actually need to divide this into little parts because the magnetic field along this part is constant. Okay? And everything else is constant, so I can just calculate the total force, and because the current and the magnetic field are perpendicular to each other, my cross product becomes a simple product. The force is going to be the length A, B. Okay, sorry about that. So this is the expression for the force, and to finalize, I also need to calculate an expression for B, and this is happening at x equals A plus B. So if I substitute that over there, then my B is going to be just B naught, B minus A plus B over B. This is just minus A, and we have B in the denominator, so this is going to be minus A square over B times I. Okay, so there's an A coming from here, there's an A coming from here, and times B naught. That's coming from over here. Okay? And this negative indicates that this is in fact opposite. It's in fact in the negative z direction, because if you choose your x and y axis this way for a right-handed coordinate system, your z axis is going to be pointing this way. Okay, I think that's all.